Now that I have established a reliably functioning design with version 7.0 of my direct granule extruder, it is time to fine-tune the hardware. The goal was to fabricate an extruder without a brass insert, as fewer parts mean simpler manufacturing, and simplicity of design is my motto. The brass insert was needed to cover the inner wall on the cold side of the extruder, which was otherwise too rough after the drilling process. Version 7.1 continues to be based on a 40mm long stainless steel M6 threaded sleeve. With a 90° countersink bit, the upper edge is widened almost to the outer diameter of the sleeve. The M6 thread is then drilled out over a length of 34mm with a 6.8mm drill bit. Next, the top of the sleeve is drilled to a depth of 6 to 8mm with a 8mm bit. At the transition between cold and hot end, material is removed to reduce the outer diameter of the sleeve to between 8 and 8.5mm. This groove is now positioned just 50mm rather than the previous 20mm from the upper edge. It is 2 to 3mm wide and serves to keep the plastic's melting zone as compact as possible. The 6.8mm bore is then enlarged using a 7mm manual reamer, a process that also smoothens the inner wall. As is typical with reamers, the diameter decreases slightly towards the tip. Consequently, the bore becomes 0.2mm narrower in the direction of the hot end. The critical requirement is that the inner wall at the cold end and within the softening zone is sufficiently smooth. A mirror smooth finish, however, is actually detrimental, as it would cause the plastic to rotate along with the screw, resulting in a drastic drop of the extrusion rate. The sleeve, having been finished with the hand reamer, provides sufficient radial resistance to enable the extrusion of the plastic. I added 3 notches to the top edge to allow the screw to grip the plastic grains more effectively. In version 7.0 I had used 8 smaller notches, however 3 are sufficient. The design for version 7.1 did not come about overnight. Once again I conducted extensive experiments during which I discovered that the basic design is highly robust with regards to manufacturing tolerances. I enlarged the bore at the upper end to a diameter between 7.5 and 8.5mm, though the extruder functioned even without this modification. However, this enlargement allows the material to be fed into the extruder more effectively. My test demonstrated that up to 20% more material is extruded per screw revolution. As previously mentioned, I relocated the groove from 20mm to 15mm below the top edge. This ensures that the cold end is sufficiently long to grip the powder and move it downward, while simultaneously increasing the reservoir of molten plastic, a factor that benefits the maximum material throughput. To facilitate more effective heating of this larger volume, I increased the length of the aluminum block with the heating element to 20mm. Let's now move on to various printing tests, starting with the maximum volumetric throughput. The material used in all tests is recycled PLA. Here I'm printing a hollow cylinder with a diameter and height of 100mm and a wall thickness of 0.7mm. The extrusion width is set to match this wall thickness of 0.7mm, while the layer height is set to 0.4mm. The maximum print speed is 30mm per second, resulting in a volumetric throughput of 8.4 cubic millimeters per second. The hollow cylinder is not printed in vase mode, as this mode is rarely relevant in practical applications. At the transition to the next layer, the motion momentarily pauses in the XY direction. The resulting seam demonstrates how effectively the extruder can transition from maximum volumetric throughput down to 0 and back to the maximum value. The printing temperature is set to 230 degrees Celsius. Printing is performed using a 0.4mm nozzle. While a slightly higher volumetric throughput is achievable with a 0.6mm nozzle, this value does not increase further when using even larger nozzles. This indicates that the greatest friction must be overcome with the cold end and the melt zone. A slightly smoother internal wall finish might therefore prove beneficial. Further experiments might confirm this. The NEMA 17 stepper motor used here has a maximum holding torque of 42 Nm, while variants with 65 Nm are available. They are significantly heavier. During the single wall printing, no gaps appear in the surface. The extruder operates reliably, maintaining a sufficiently consistent volumetric throughput. The excessively loud squeaking and cracking noises do not originate from the extruder itself, but rather from the second external stirrer located in the front section of the hopper, where an excessive amount of plastic dust has accumulated on its rotational axis. Only very rarely the clicking sound of a skipped extruder motor step can be heard, a phenomenon that demonstrates two things. First, that the extruder is indeed operating at its absolute limit, and second, that the material feed is subject to minor statistical fluctuations. More on this in the upcoming video. The print is completed after 45 minutes. In the second run, using identical print parameters, I determined the maximum achievable temperature. At maximum volumetric flow rate and with the part cooling fans running at 100% power, a temperature of 260 degrees Celsius is attainable with the original 40W heater cartridge from the Bruiser Mark IV. The next cylinder is printed with an extrusion width and wall thickness of 0.5mm, settings that align more closely with the typical requirements of a compact printer like the Bruiser. The layer height is set to 0.2mm, my standard value for printing with this machine. Once again, the print speed is set to 30mm per second. This results in a volumetric flow rate of 3 cubic millimeters per second. This is a setting typically used for printing fine details, and, as expected, the extruder handles it with absolutely no difficulty. The print takes 90 minutes to complete. The next cylinder is printed at 80mm per second, with otherwise identical parameters. The maximum volumetric flow rate increases to 8 cubic millimeters per second, which is again close to the limit. Here too, the extruder works flawlessly and no gaps appear in the outer wall. The extruder was designed from the beginning to print fine structures on a compact device, and it does this very well. Plenty of pellet extruders with high volumetric throughput for large printers are already available, but they don't produce prints with nearly the same level of detail as this extruder in version 7.1. It takes 36 minutes to complete the printing of the third cylinder. Let's take a closer look at the results. Only dust particles but no gas bubbles are visible on the outer walls of the first cylinder. This shows that the idea of a gap between the screw and the extruder wall works well, allowing the air to escape. I might clarify in a later video to what extent water vapor could cause gas bubbles. The PLA powder sat uncovered in my basement for weeks and wasn't dried before printing. The first cylinder with a 0.7mm wall thickness weighs 28 grams. Assuming a density of 1.3 gram per cubic centimeter for PLA, this corresponds to the theoretical value. Cylinder number 2, printed with a 0.5mm wall thickness, weighs 21 grams. Theoretically, 20 grams would be expected. Finally, cylinder number 3 weighs 20 grams. Due to the higher flow rate, slightly less material came out of the nozzle, but overall, the slippage in the extruder only increased very slightly. Let's take a look at the seam, which is rather thin on all 3 cylinders. I performed the same test with the Bruiser using the original filament extruder. and the seam is much more prominent there. A plus for the harder steel of the screw compared to the plastic filament. The next test examines stringing. 3 cones are printed, each with a 10mm diameter at the base, 1mm at the tip and a height of 30mm. These are arranged on a circle with a 40mm radius, resulting in a distance of approximately 70mm between 2 cones. The extruder performs the retraction by changing the direction of rotation of the screw, which transports material upwards in the tube. In addition to the printing parameters, it is important that the screw is inserted deep enough into the softening zone of the extruder tube. In version 7.1 this is currently only 26cm, as the tube is mounted 5mm lower. With a now longer hot zone I could increase the insertion depth back to 31mm by removing spaces, but I would first have to print and install a flatter steerer. Overall, only a very few very thin strings appear between the cones, which can easily be removed by hand after printing. This brings us to bridging. I am printing a structure with 5 bridges spaced 8mm apart vertically, with length increasing from 8mm at the bottom to 65mm at the top. During bridging, the back pressure at the nozzle tip drops abruptly right at the edge where the nozzle transitions into the gap. The extruder evidently handles this very well. Furthermore, the extrusion remains sufficiently consistent to ensure that none of the strands snaps. In principle, bridging works without any problem. The extent to which the unsupported strands sag depends not only on the extruder, but also, among other factors, on the cooling provided by the fans. I didn't engage in too much fine-tuning here. For now the focus is solely on the extruder, not on the combined performance of the extruder and the printer as a complete system. Next up I'm going to print some track links again. The first link is printed at a speed of 30mm per second with an acceleration of 500mm per second square. With its thin 2mm walls and straight edges, this print test serves as an excellent indicator of whether the plastic is being extruded uniformly. Version 7.1 performs quite well in this regard, though there are few spots where individual layers stick out slightly. The extrusion process is inherently statistical in nature and is dependent on the specific properties of the plastic powder being used. I will explain how to achieve even smoother walls in my upcoming video, which focuses on the properties of plastic powders. Track link number 2 is printed at a speed of 80mm per second. However, this maximum speed is reached only at the infill, which is processed at an acceleration of 10,000mm per second squared. For the third track link we go full throttle. The acceleration is set to 10,000mm per second square, even for the outer structural elements. The printer's mechanics visibly vibrates and the resulting print quality suffers accordingly. With the third test I wanted to see whether the lower extrusion rate at higher throughput would cause any visible gaps in the walls. This is not the case, however mechanical vibrations are clearly visible as a wave pattern on the walls. These vibrations are due to the 1037 grams of total mass that must be moved along the x-axis. Even on the second slowly printed chain link, the edges of the walls are not as sharply defined as they could be with a 0.4mm nozzle. This is partly due to slight over-extrusion during deceleration just before printing the band, and of course to mechanical overshoot caused by the moving mass. This can be improved using pressure advance and input shaping, however implementing these features on a bruiser is tricky, which is why I still do not use them. In a later upgrade phase I will switch to my Retract vCore 4 and implement these parameters at that time. The eagle-eyed among you may have noticed a specific defect while printing the bridging structure. The edge where printing resumes after a retract shows small gaps. I'm showing this phenomenon more closely with another test. Two blocks are being printed spaced 10mm apart. Particular attention should be paid to the left block where printing on the front face resumes, moving from left to right immediately following a de-retract. This is precisely where the aforementioned small gaps occur. The root cause lies in a small blob of material that forms at the print starting point due to excessive plastic extrusion. During a retraction, the extruder screw is rapidly rotated backward by a specific angle, let's say by 1 full revolution. During the subsequent de-retraction, a rapid forward rotation occurs over the exact same angle, again 1 full revolution. Theoretically, the volume of material lifted up inside the tube during retraction should equal the volume subsequently pushed back down during de-retraction, yet material oozes out of the nozzle tip. But why? Well, during a retraction a small amount of air is drawn into the nozzle. Some of this air then rises up through the extruder as the molten plastic flows downward under the influence of gravity. Consequently, during de-retraction, the plastic that gets extruded is the material that had flown towards the nozzle, driven by gravity during the retraction phase, and the print heads travel to its next destination point. The blob that forms at the point of de-retraction is located along the inner surface of the two outer perimeter walls. As the printer subsequently prints the outermost perimeter and moves over this blob, it induces vibrations. This results in the formation of a protruding edge followed by a visible gap. The parameter that needs to be adjusted in bruiser slicer is extra length at de-retract. This value must be set to a negative figure, in my specific case -1mm. What this approach fails to account for is that, immediately afterward, for a distance of a few millimeters, slightly too little material is actually extruded, as the previously drawn in air completely exits the extruder again. Addressing this would require implementing new parameters in the software. Thanks to the negative value applied during the de-retraction phase, at least no blobs are printed anymore and the edges turn out clean without any gaps. And that concludes my current update on the ongoing development of my direct granules extruder and the specific nuances involved in printing with it. To wrap things up, rather than running another test, I'm here printing a gear that I need for another project. As always, the build instructions for Extruder 7.1, including the 3D files, are available on my website. You'll also find a donation button there, which you can use to send me a thank you for all my efforts on this open source project. A big thank you to everyone who has already made a donation or supports me via Patreon. Again, a special thank you to my anonymous major sponsor. Thanks for watching and I'll be back.